Linear transformations or matrix transformations are studied a lot in the early years of linear algebra. They map from one vector space to another vector space. Usually in first year, it is from a real vector space Rn to another real vector space Rm. So I denote my linear transformations as capital L. A lot of times, actually, you see it as capital T. So you have Rn to Rm. However, in general, you don't have to have it where it's real vector spaces mapping to real vector spaces. It could just be any vector space U mapping to another vector space V. For example, the space of polynomials, matrices, real vector spaces, etc. Okay, so I'm just going to generalize it. So L is a linear transformation mapping elements from big U to big V. So I'll say the element U is going to be mapped to an element L of U, which is equal to V. Okay. So L is a linear transformation, and it satisfies 2 to 3 properties, mainly 2 properties. The third one follows from the first two. So the first property is L of x plus y is going to equal to L of x plus L of y for every x and y in U. Okay. And the second property is L of c times x is equal to c times L of x for every x in U and for every scalar c in real number. And it follows that L of 0, I'll just say 0u is equal to 0v. So this is always true. L of 0u maps to 0u maps to 0v. Okay. L sends 0u to 0v. And this is true because if you have L of 0u, that is just equal to L of, let's say, little u minus little u, where little u is in the vector space big U. And then this is equal to L of u plus L of minus u, or negative u, which equals to L of u minus L of u, and that gives you 0v. Because L of u is just some, let's say, v, right, in big V. So some little v and big V, and we have v minus v, little v minus little v, that's just 0v. So here, this is due to property 1, this is due to property 2. Okay, so that's that. I'm mostly interested in this theorem where you have it where a linear transformation L is injective if and only if the kernel of L is simply just 0u. Okay. And by the way, the kernel of L is simply just the I would say it's defined colon equal, okay, defined to be the set. We first define it first, and then you can use the equal sign, but we define it to be the set of all little u in vector space big U, such that L of little u is equal to 0v. Okay, so all the u's in the domain, all the input u's that give you an output of 0v. So pictorially, if you have u and v, and this is going to be, let's say 0v, and then here I have some whatever points, something like that, that all map to 0v under the linear transformation L. Okay, so this is, and of course, the 0u is in the kernel of L. 0u is always in the kernel of L due to this property 3 right over here. Okay, but we're saying that if L is injective, then the only thing that is in the kernel of L is 0u. Okay, so that is that. So when L is injective, then you have it where only this part gets mapped to 0v. Okay, only 0u gets mapped to 0v. Okay, and for injective, another way to say injective is 1 to 1. Okay, and it just means that no two inputs can give you the same output. So y is equal to x squared is not injective because you have two different inputs, let's say -1 and 1, but they both give you an output of 1. So the y value is 1. So this is not injective or 1 to 1. You can say that it fails that horizontal line test. But then let's say if this is like y is equal to x plus 2, then this is going to be injective. You give me any two inputs, right? They're always going to have the same, different output. Okay, so that's injectivity. So in general, if you have L is injective, so L is injective. It's more like you can say it's a definition, right? L is injective, if and only if I have, let's say, L of u1 is equal to L of u2, then that means that, so if the outputs are the same, then the inputs have to be the same. u1 is equal to u2. Okay. I could consider this as like a definition, right? Definition, okay, is biconditional anyways, but over here I could add the backwards arrow right here, but that is trivial because if the inputs are the same, the outputs are for sure going to be the same, but we're mostly looking at this direction because if the outputs are the same, then the inputs are the same, then we have a injective function or linear transformation. That's what we're dealing with here. Okay, a linear transformation is just this special kind of function, okay, that we're dealing with in linear algebra. So that's just a definition to keep in mind. So I'll start this. Anyways, we'll start with the proof in one direction. Okay, so the forward direction, we have it where L is injective. This implies that the kernel of L is only 0u. So, well, let's see. We know that L is injective. That means we know that L of 0u, that is equal to, suppose it's equaling to, let's say, some other little u and big U, right? which is equal to 0v. Okay. So L of 0u is always going to be 0v, but let's say that equals to L of little u, arbitrary u, little u. We don't know what little u is. Then what we have is that u, 0u, well, L is injective, right? So if the outputs are the same, which gives you 0v, then 0u, the inputs have to be the same, so 0u has to equal to little u, right? So what does that mean? It means that give me any arbitrary u, I don't know what u is. If L of u is also 0v, then we get that u is 0u. Okay, so we get that kernel of L is equal to all the u's that get mapped to 0, but we see that you give me any u, arbitrary u, in the end it's that u is just simply always equal to 0u, so we get it's just 0u. 0u is always going to be in the kernel of L, but in the case when L is injective, there's no other elements distinct from 0u. All other elements are the same, right? If you have another element, let's say u, in here, we get that this u is 0u, and in the set, you don't repeat elements, so that's what you have. Okay. So now the backwards direction. Okay, so the backwards direction states that if kernel of L is equal to 0u, then L is injective. Okay. When we have it where the only thing that maps to 0v is 0u, then it is necessarily the case that L is injective. Okay, so we'll see why that is true. So our first assumption is kernel of L is just 0u. Let's have it where we have L of let's say I have L of, I'll call it L of x, okay, where x is in u, and that is equal to L of y, where y is also in u. If L of x is equal to L of y, this implies that L of x minus L of y is equal to 0v. What does this imply? I should probably take a note here that x and y are in u. Okay, but I guess that's already known. Okay, that's assumed. This implies that L of, well, if you combine properties 1 and 2, if I guess you're going in the other direction where you kind of like combine everything instead of like breaking it apart, you have L of x minus y, right? That is equal to 0v. Okay. So what does that mean? It means that x minus y, it has to be in kernel of L, right? Because L of something gives you 0v, that means this something has to be in the kernel of L, because the kernel of L are all the elements that map to 0v. So here is an element that maps to 0v, right? So x minus y is in the kernel of L. But we said that in this backwards direction, that the only thing in kernel of L is 0u, right? Which means that x minus y is equal to 0u, right? Which implies that what does this imply? If you move the y over, then you have that x is equal to y. Oh, wait. We started off with two outputs equaling to each other for arbitrary elements x and y, for arbitrary input elements, right, inputs x and y. We have it that the outputs are the same, but that implied that the inputs are the same. Isn't that the definition of injective, right? The outputs are the same implies the inputs are the same. That means the function is injective, or here the linear transformation is injective. And that is true because we know that the kernel of L is 0u for this case right over here. Okay, so this implies that L is injective, or L is one-to-one. Slash 1, 2, 1. Okay, so that is it. And so now this is a very interesting concept to prove, and hopefully that makes sense, and you can just basically use this theorem to show if a certain linear transformation is injective or not. This is the result, right? This is the theorem. But in this video, I was just going over the proof for both directions. Okay.